We are looking at solving trigonometric equations. We're solving for a variable theta that is stuck in the argument of trigonometric functions, and we need to try to find the value of theta that solves this equation. The first thing that we'd like to notice on this one is that I have an angle theta in the argument of cosine, but then negative theta in the argument of sine. So that's initially something that's a little problematic. We'd like to see the same angle theta in the argument of our trig functions. That's going to enable us a lot more options. So let's recall that the sine function is an odd function, which means if I'm looking at the sine of negative theta, that's the same thing as the opposite of the sine of theta. So I'm going to choose to use negative sine theta as a substitution for sine of negative theta. So this makes our equation turn into cos theta minus sine of negative theta is the same thing as the negative sine of theta. So we'll substitute that in for this guy, and we end up with now the cosine of theta plus the sine of theta is equal to 0. Now, we kind of get stuck here just a little bit because, generally speaking, I like to be able to factor a trigonometric equation in order to be able to set each factor equal to 0, or I like to be able to substitute sine for cosine or cosine for sine, but in that case I would need to have a cosine squared or a sine squared as part of the problem, but I don't have that either. So one way we can proceed is to just think about this on the unit circle, to say if I'm going to have a cosine and a sine that add together to be 0, that's going to occur when the cosine and the sine are the same value except for opposite in sign. So the angles where the cosine is negative radical 2 over 2, positive radical 2 over 2, and vice versa, where I have the cosine positive radical 2 over 2 and negative radical 2 over 2, these two angles will have the cosine and the sine adding together to give me 0. So who are these angles? Well, in the second quadrant, the angle is 3 pi over 4, and in the fourth quadrant, the angle is 7 pi over 4. So we're expecting these to be our solutions for the theta values where the cosine and the sine would add together to give me 0. But let's think about the same problem from a different perspective, because it's not always as easy to see what the answer must be, and to have a process by which we can calculate it will serve us a little bit more. So the goal here is to get this equation entirely into sine or entirely into cosine so that I can make a substitution, hopefully ending up with a quadratic form equation, making a u substitution and factoring it. We'll see what happens, but how do I get into an equation where I'm able to substitute into sine or cosine? Well, I need to have a cosine squared or a sine squared, and so what we'll do here is to subtract sine theta from each side to end up with cosine theta is equal to minus sine theta. Now, in order to get a cosine squared or a sine squared, or in this case we're actually going to get both, it is allowed for me to square both sides of the equation in order to get into cosine squared or sine squared. So I end up with this equation now, and I am able to use a substitution to get entirely into, let's go into sine this time. So in order to get entirely into sine, I would need to substitute 1 minus sine squared theta in for cosine squared, and then on the right hand side I'm going to have sine squared theta still. So now I would like to set this thing equal to 0 and see what happens. So let's subtract sine squared from both sides, and we end up with minus 2 sine squared thetas plus 1 is equal to 0. Now, this is again quadratic, so if the sine squared theta is off-putting, you could make a substitution and let u be equal to sine theta to kind of simplify this a little bit, in which case you would end up with minus 2u squared plus 1 is equal to 0, and you could use your regular quadratic methods in order to solve for u and then back substitute into sine. I'm going to continue to work with the sine squared theta instead of making that substitution. So noticing that it's quadratic, we actually do have several options to us. We could try to force factor this thing, but what I would choose to do is use the square root method here. I'm going to add 2 sine squared theta to both sides, so that we end up with 1 on the left and 2 sine squareds on the right. Then let's isolate the quantity that is squared by dividing both sides by 2, so that we end up with 1/2 is equal to the sine squared theta. So before we can access that value of theta, we want to isolate the sine, so I want to take the square root of both sides. So we take the square root of both sides of this equation. Again, this is essentially the square root method. You could have substituted a u in for sine theta, and you would end up with 1/2 is equal to u squared here. We'd be solving for u. We're choosing to continue to work with the sine just to avoid a couple of extra steps. Again, when we take the square root of both sides, we do need to consider the plus or minus, so what we end up with is that sine theta is equal to plus or minus 1 over the square root of 2, which is a number that we recognize more often when we see it in its rationalized form. This is the same thing as saying sine theta is equal to plus or minus radical 2 over 2. So who are the angles whose sine is radical 2 over 2 positive or radical 2 over 2 negative? These are known angles. They are my pi over 4 guys. I have a positive radical 2 over 2 sine in the first and second quadrant. I have a negative radical 2 over 2 sine in the third and fourth quadrant. So what we end up with values for theta are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now you may notice that that's more angles than what we originally ended up with. We originally ended up with just 3 pi over 4 and 7 pi over 4. So we've got a little bit of a discrepancy that needs to be considered. So let's check our answers. Let's start off with the 3 pi over 4 and 7 pi over 4 answers. So we enter in 3 pi, divide that by 4, and make sure that we store that into our variable x. We also want to ensure that we're in radian modes, and we are, so we should be good to go ahead and evaluate this trig expression at the value of 3 pi over 4. So we want to take 3 pi over 4, store it into x, and then type in the left-hand side of the original equation in order to see if this is a working solution. So the cosine of the value that we have stored in x minus the sine of the negative value that we have stored in x, or the opposite of the value we have stored in x, and we see what this is equal to, and it turns out to be 0. So 3 pi over 4 is a working solution. Let's check 7 pi over 4 by typing in 7 pi, divide that by 4, and then store that into the variable x. Select enter to ensure that that angle is actually stored in x, and then we want to copy paste the expression that we've already entered into our calculator by hitting second enter and then second enter again. We do it 2 times in order to get not the most recent entry but the one before that. Now I'm going to hit enter again to evaluate that expression at the new value of x, 7 pi over 4. We notice that when we evaluate that expression at 7 pi over 4, we get some very strange value, 2.1 e negative 13. This is a little unexpected. We were expecting for the value to be 0, but 2.1 e to the negative 13 is the calculator's way of using scientific notation, saying 2.1 times 10 to the negative 13. That's the same thing. Well, 10 to the negative 13 is a very small number. So what we're looking at is truly 0.1 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places to the left that we move our decimal. So what the calculator gave us was a value that was extremely small, very, very close to 0. Sometimes when we enter an irrational number into our calculator and we evaluate an expression at an irrational number, the calculator will return a very small value, very close to 0, when it means to say 0. So we could calculate this by hand to get an exact value of 0. The calculator is giving us this decimal instead of saying 0, but it actually means 0. So 3 pi over 4 and 7 pi over 4 were both working solutions. So let's go back to the other two and see what happens. We also want to check pi over 4 and 5 pi over 4. So let's enter pi over 4, store that into x, and then second enter once to get the most recent entries, second enter twice to get the one before that, and then we select enter for another time to see that this value is not 0, nor is it a decimal that's very, very close to 0. This is 1.414. That's the same thing as the square root of 2. So when we plugged pi over 4 into the original expression, it returned a value of square root of 2 instead of returning a value of 0. That means that pi over 4 doesn't work. It doesn't give us the value that we were expecting. And so we generated an answer that didn't work, which is something that we've seen happen before in algebra. This is an extraneous solution. So now let's check 5 pi over 4, our last solution. We have 5 pi over 4 stored into the variable x. We're going to hit second enter 2 times. Actually, I think we'll need it 3 times in order to get back to the expression that we want to evaluate. And then we hit enter with 5 pi over 4 stored in, and this is negative radical 2. So we see that 5 pi over 4 does not work either. We had 2 extraneous solutions, and we had 2 solutions that actually checked. So our solutions to this equation were 3 pi over 4 and 7 pi over 4, and that's it.